Hello there, this is a video on benzene. So we're looking at here the chemistry of benzene. Okay, now there's a lot on this video that I'll tell you about the basics in benzene, but it might be a bit complex. I don't know. I don't know the depth to which you look into benzene. Okay, so let's have a look at it first of all. Well, benzene is a six-membered carbon ring like this. Okay, and each carbon is attached to one hydrogen like this. Okay, and to get the bond numbers correct, we put a double bond every second bond like that. Okay, so this was originally thought of as the structure of benzene like this. If this were the case though, these double bonds would be shorter than the single bonds. Whoops, it would look something like this if this were the structure. Okay, it would look like something like this. Okay, in other words, with three short bonds here, this is the double bond, this is the double bond, and this is the single bond. And it doesn't look like that. All the bond lengths are the same. So something is obviously happening. And what happens is something called delocalization. So the electrons kind of overlap with each other around the system here. Okay, so the way we draw benzene now, this gives it the cyclo bit, the ring structure, and we put a circle in the middle, and this circle represents this guy here. This represents what we call the delocalized ring system. Okay, and as I say, it's delocalized. All right, now some technical stuff now. Let's move this up a bit. Okay, and let's draw it. What does the delocalized ring system mean? Well, there's a carbon. Let's redraw the benzene a bit bigger. Okay, now this stuff might maybe I don't know if you know what I'm going to talk about now, but it's how benzene does what it does. Okay, there we go. Right, now benzene, these bonds in benzene are what we call sp2 hybridized. Okay, now I'm not going to talk about what that means for now, but it means it has a shape of trigonal planar. In other words, it's flat and it's trigonal planar. It's flat and it's got three directions. So benzene is a planar molecule. Okay, and the hybridization here between carbons is sp2 hybridized. So let's draw those in. Okay, again, I don't know if you do this stuff, but we'll figure that out later. So there's an sp2, there's an sp2, there's an sp2 from this one, sp2. It has three sp2 orbitals, like that. Okay, there we go. They overlap, and there's one going out to the hydrogen. And then the hydrogen has its s orbital, okay, which overlaps with the sp2 from the benzene, okay, from the ring system. All right, now if you've got sp2, only 3 electrons are being used in the sp2, and as you know, carbon has 4 electrons in the outer shell, so that means there's 1 electron, let's try a different color, 1 electron that's not being used, and this is in the p orbital. So let me draw the p orbitals here. These are the p orbitals. Now, I'm trying to draw something three-dimensional on a two-dimensional surface here, so it's a bit complicated, but never mind. We should be able to get the idea of it. Okay, so these p orbitals, now what do? They overlap with each other. So this would have been the original double bond, the structure I originally drew. So the p orbitals overlap with the p orbitals like this, side-on bonding. So these would be pi bonds, wouldn't they? What happens though is if you alternate single and double bonds, the electrons overlap with each other. They delocalize. So this will now delocalize with this one. This one will delocalize. Where are we now? This is the top. This one will delocalize with this one, and this one will delocalize with this one, and the bottom will. These lobes will delocalize with each other like that. So you get electron density above the ring and below the ring. So if we looked at a benzene molecule from the side on, this is a side on view. Oops, what on earth is that colour? This is a side-on view. Side-on view. If you look at benzene from the side, you'll get these. From the side, you'd only see 4 carbons, wouldn't you? Because you wouldn't see the ones at the back. You would get electron density at the top. Funny colour again. And electron density at the bottom. So this is extra electron density. This is electron density. We have a lot at the top, and you have electron density at the bottom. Okay, now this informs how benzene reacts, because when benzene reacts, it is very negative on the top and on the bottom, and it attracts electrophiles. Okay, so let's try a different color, red, I think. An electrophile is going to hunt for these negative centers and electrophile down there, so it can be attacked from the top or the bottom of the ring. Okay, so that's basically how benzene reacts. Okay, the electrons on the top, because of the delocalized system, and the electrons on the bottom provide an increased electron density, and this electron density will attract electrophiles, and that's how benzene reacts. All right, now beforehand we looked at these double bonds, these so-called double bonds. These are pi bonds, aren't they? These would be pi bonds. Now, but when they delocalize in benzene, the pi bonds delocalize over each other, and they become something quite special, and this is known as a pi system. Okay, and that's, whoops, this is a pi system, and when we draw a benzene these days, we draw that, and the circle represents the delocalized pi system. All right, so that's that. I won't do too much more today because this is quite complicated already. So let's have a look then with benzene. Now, substituent groups. All right, these mean these are things that are on the benzene. Okay, now let's have a look at 2 groups on the benzene. First of all, let me get rid of this awful color. All right, it's to draw my benzene here. All right, let's draw another benzene here. 2 benzenes. Okay, the top benzene, I'm going to put a CH3 on, and the bottom one, I'm going to put an NO2 on. Now, the top one, if we've got a CH3 on, is known as methylbenzene. Okay, old name for methylbenzene, or the name, is toluene. All right, bottom one is called nitrobenzene. All right, now these are substituents. Okay, that means they're stuck on the benzene ring. We'll talk about how we get them on there later, but this is just something kind of interesting about benzene. Right, with the methyl group attached. Okay, let's get this is a nice white color. The methyl group attached. Now, electrons are drawn or pushed from the CH3 group into the benzene ring. So we say the CH3 group, it pushes electron density onto the ring. Pushes electrons onto the ring. Okay, we say it has a positive inductive effect. Okay, because it pushes electron density onto the ring. The nitro group pulls electron density off because nitrogen and oxygen are very electronegative. It's hard writing on this, actually. That's why it's not very good. Very electronegative, and they withdraw electron density. Okay, from the ring. All right, and this is called a negative inductive effect. Negative inductive effect. Okay, we often simplify this by saying these are plus I for inductive effect, and these are minus I for negative inductive effect. Now, what are the oopsie daisy, didn't go well, did it? What are the consequences of this? Well, in the case of methylbenzene, oopsie daisy, methylbenzene. I don't know what's going on there. My pen seems to be going a bit weird. In the case of methylbenzene, all right, it's not right. Let's get rid of that. For some reason, it's going a bit weird today. In the case of methylbenzene, if we have a look at the side on now, we'll get something like this. And in the case of nitrobenzene, let's try and keep the colors consistent. Let's use this color for, this is going to be methylbenzene, and this is going to be nitrobenzene. If we look at the side-on view, as we looked at earlier, okay, within methylbenzene, electrons are being pushed on. This is this top one, if you remember. Electrons are being pushed onto the benzene, and therefore the electron density will be enhanced in methylbenzene. You'll get more electrons above and below. So in methylbenzene, excuse me, you will get increased electron density in the ring. Okay, and in methylbenzene, sorry, in nitrobenzene, you're going to get less electron density. I'm drawing it just by these funny looking things here. But you're going to get decreased. Here, we get decreased electron density. Now, what does that mean then? So if I have nitrobenzene, I get increased electron density, and if I have methylbenzene, I get increased electron density, and if I have nitrobenzene, I get decreased electron density. Now that means for a visiting electrophile, an electrophile that wants to attack, an electrophile might be something like a Cl plus ion, and if you have an electrophile attacking this one, electrophile, let's say a Cl plus again, attacks this, obviously, I think you can see here, the attack here is going to be promoted because there's more electrons here than there are here. So if I have methylbenzene, it is going to be more reactive. All right, and we say the methyl group, promotes the reaction, but we use a special word for that, and we say it activates the ring. In other words, increases the reactivity. With something like nitrobenzene, it decreases the electron density, and therefore nitrobenzene tends to deactivate the ring. Okay, there you go. Now I'm going to stop the video there, and I'm going to ask for comments because I just genuinely like to know if this is the kind of level you need or a little bit more specific stuff. Okay, all right, let me stop the video and have a nice Christmas.